This is my video lab report for Lab 3 for Physics 2211 at Georgia Tech. So the premise of this lab is to estimate the mass of the black hole around which a star is orbiting. So we're given a data file that contains the star positions, about 1,000 of them, in the x and y coordinate system. We're also given the star mass and the time step, which is 1 day, equivalent to 86,400 seconds. We're also given the position of the black hole. We use Newton's second law to estimate the momentum change and the forces in this system. And the end result was the black hole mass was approximately 3.98 times 10 to the 31st kilograms, which is roughly equivalent to 7,027 stars as the one in our system, or about 20 of our suns. So here are some of the equations derived from Newton's second law that were used to formulate the code in Python. And below that is the law of universal gravitation, which is used in the end to find the actual mass. If we want to take a quick look at the Python code, we can run it to see the simulation. So you can see from the model that the parallel component of the momentum, or the net force, initially started off pointing in the positive x and y direction, but by the end of the model it's pointing in the negative x direction because it is past the black hole already and is decelerating. And you can also tell that the yellow arrow, which denotes the total net force, is always pointing to the black hole. So you saw the model and how that worked. The way that the momentum was calculated was through a derivative estimation of the velocities, which was then compiled and extrapolated into a net force. For each run of the program in Python, it generated a new mass of black hole. These were all averaged, which is where I got the average black hole mass. So now there are a couple of questions I'd like to address. A lot of times, net force and change of momentum are assumed to be the same thing because their numerical values are the same. However, they are not the same thing. The change of momentum is the effect of the net force. So they are not actually the same thing. One is the cause, one is the effect. They just simply have the same numerical value. And that's true for the net, the parallel component, and the perpendicular component. They each are cause and effect of each other. Next, what if a black hole was exchanged, but the motion was not affected at all? Now, if this happened, you would not be able to tell the difference, because with the motion unchanging, that means that all the calculations that went into calculating the net force in our program would be the same. If all those calculations are the same, that means that the mass of the black hole is the same, in which case there really is no difference. It's a different entity, if you will, but the effect of it is the same, and you wouldn't be able to tell the difference from our viewpoint here. So one last quick rundown here. We're given the star positions, time, star mass, and black hole position, and we need to find the black hole mass, which is related to the net force. So we use approximate velocity derivatives from the position versus time data, multiply by mass to find momentum, approximately derive that again to get the change momentum. From that we could calculate the net force and its components from momentum and its components. And using that net force we could solve for the mass of the black hole using the law of universal gravitation.